Today we will be exploring the relationship between electric field and electric potential. But first, to do this, we must understand what an electric field is. The electric field lines that come out from an electrical charge always flow from an area of high potential to an area of low potential, or in other words, from a positive charge to a negative charge. So we can see if we replace this positive charge with a negative charge, all the electric field lines flow towards it. Now let's move on to electric potential. The textbook definition of electric potential is the amount of work needed to move a charge from a reference to a specific point inside a field without producing an acceleration. What in the world does that mean? In simple terms, work equals the charge times the change in voltage from A to B. In this example, we can show you just what it means. Plate A is positively charged, and plate B is negatively charged. The potential difference in the charges from plate A to plate B is voltage. Now we can examine the situation with our two plates, where we have the field lines going from positive to negative. And when we place our charge in there, the forces acting on the charge are pulling it towards the negative side. The attraction between positive and negative pulls it to the negative side, and the repulsion between the positive plate and the positive charge also push it towards the negative side. This is analogous with the situation of the Earth. We have the Earth and a ball above the Earth. Gravity pulls down on the ball, pulling it towards the Earth. So we can see that the ball wants to move in a downward direction. In the situation of the Earth, we have potential gravitational energy. But in the situation of our electric field, we have electric potential. Now that we understand both electric field and electric potential, we can begin to look at them together. When we add a point charge in space, that charge has an electric field, shown by the electric field lines, which are vector quantities, meaning that it has both magnitude and direction. It also has voltage, which does not have direction, but it does have a magnitude, which depends on the distance away from the charge. The relationship between electric field and electric potential is given by the equation E equals negative delta V over D. D is also sometimes replaced by delta S, but they mean the same thing. In our equation, E is the electric field, given in units of newtons per coulomb or volts per meter. Delta V is our change in voltage, and D is the distance from the charge over which the change in potential takes place. The negative in front of delta V means that the electric field points in the direction of decreasing potential. Now let's find the electric potential difference in this system. Let's say that the distance away from the charge is 0.5 meters, and the electric field strength is 10 volts per meter. We will use our equation that relates electric field strength and electric potential together. We can now rearrange our equation and plug in our numbers to solve for the electric potential at the distance 0.5 meters away from our charge. We now see that the change in potential over our distance d is negative 5 volts. In another example, we will examine the relationship between electric field and electric potential in between two plates. In these plates labeled A and B, we see that the electric field travels from plate A to plate B, or from an area of high potential to an area of low potential. In this example, using the two plates, we will use our equation for the relationship between voltage and electric field to determine the maximum voltage between the two plates. In this example, our D is the distance between the two plates. Our negative in front of the delta V once again reminds us that the electric field flows from high potential to low potential. For finding our delta V, we subtract the final voltage from the initial voltage, meaning that we subtract VA from VB, but the negative in front allows us to switch those two so that it becomes VA minus VB, which gives us our change in voltage VAB. Now we can place that into our equation, making our new equation E equals VAB over D. Now continuing on in our quest to find the max voltage, we are given that the electric field strength is 3.0 times 10 to the 6th volt per meter. We are also given a distance of 2.5 centimeters, but it is important to remember that our equation calls for meters and not centimeters. Therefore, we must convert it to be 0.025 meters. Now rearranging our equation and inserting our given values, we are able to find the maximum voltage between these two plates. And that maximum voltage is 75,000 volts, or 75 kilovolts. In summation, the relationship between electric field and electric potential can be defined by the equation E equals negative delta V over D. It is important to remember that an electric field will not exist unless there is an electric potential difference. Here is an example of how electric fields and electric potential are used in everyday life. Consider a small bird sitting on an open electric wire. The bird doesn't die because the electric wire is at the same potential, meaning that there is no difference in potential energy along the wire. Now consider an electric fly swatter. The fly swatter has two metal nets that are in close proximity to each other but are not touching. This maintains a potential difference between the two nets, which means that if a fly or mosquito comes and touches the net, it dies of an electric shock, because there was a difference in potential energy between the two nets. I hope this video was helpful in understanding the relationship between electric field and electric potential. More information on the subject can be found in the College Physics textbook, Chapter 19.2, Electric Potential in a Uniform Electric Field.